We also have Don Lam here with us, the other co-recipient of the Dawson Award. Farhad, it's a real pleasure to be addressing this group of people for the CMEC monthly seminar. In today's talk, and thank you for the introduction. It was very kind of you. In today's talk, I will discuss a little bit on the recent work that we're doing with Flash in terms of expanding its capabilities to accurately model magnetized plasma experiments. And before I start, I want to acknowledge the continued support that we have from the US DOE, ARPA-E, the US DOE Office of Science, the US DOE NNSA, and the National Science Foundation for the work that I'm about to show you. The work that I'm about to show you is actually the coming together of a number of people working on both in the development of the Flash code, but also in the execution of a number of very interesting magnetized plasma experiments, which we will cover. This is the overview of the talk. I decided to break this up in three parts. The first one to give you essentially 40,000 feet view of what Flash code is and what the Classroom for Computational Science is. And then I will give you a very brief, as far as I can, equation-free, well, there are some equations, primer into the Flash code and into the extended MHC capabilities that we've been adding into Flash. And I will wrap the talk up with three case studies in magnetized plasma experiments. One is going to be laboratory astrophysics and the effort that we're doing for the Turbulent Dynamo collaboration, TDYNO for short, which we're essentially trying to understand the origin of cosmic magnetic fields and understand how magnetized turbulence can be an agent in astrophysical phenomenology. I will talk a little bit about magnetized HDP and the work that we're doing for the Center for Modern Extreme Conditions. The Flash Center is one of the nodes of CMEC, and we're delighted to be part of this effort because it not only allows us to help the overall thrust of CMEC, but also engage and network with all of our colleagues in the field. And I will end up with applications that have to do with magnetized fusion and applications that have to do with the ARPA-E beta program. So without further ado, let's get started. So let's start with what is Flash code. Flash is, and you can see here the original paper of the code, is a publicly available high-performance computing, adaptive mesh refinement, finite volume, Hydra, and MHC code. This code has extended physics capabilities that allow it to be employed in a number of different applications, ranging from computational astrophysics to CFD, and more recently to high-energy density physics. The code development and the work that we're doing at the Flash Center is supported primarily by the US DOE and NSA, and more recently we're directly funded by the Los Alamos National Laboratory and the Lawrence Livermore National Laboratory. The code has been in continuous development for 20 years. I mean, you can see that the original paper was published in 2000. And as such, you can hardly find a line in the code that is much what it was in the beginning. So this continuous development is done adhering to strict coding standards. We have the code under version control, and we're using automated regression testing to ensure that our continuous development by the team meets the standards of the code. And we have also extensive user support in order to help new users to pick up the code and apply it for their problems, but also integrate extensive code contributions that come from external teams. To date, we're measuring up to more than 3,500 users worldwide, and more than 1,200 papers have been published using Flash in a different range of applications. And here's the team. So one thing that you will notice is that I have now the Meliora logo instead of the University of Chicago logo. 2020 has been, apart from a very hard year for everyone due to the pandemic, it has been a transition year for the center as well. We have moved essentially along with all of our funding and all the academic track scientists in the center to the University of Rochester at the Physics and Astronomy department, where now I was offered essentially an associate professorship, and we moved our operations here. The team is made up by Adam Reyes, who's the code group leader, and 3 postdoctoral scholars, Eddie Hansen, David Michta, Ying-Chao Lu, and 3 graduate students, Marissa Adams, CJ Armstrong, and Kasper Moksulski. Definitely destroyed his name. I apologize, Kasper, if you're on. Of course, Don Lam is still very much involved with the center in both our research and our operations. And what we do essentially amounts to what this mini flyer tells you here. So we're essentially studying astrophysical processes by developing the flash code, applying the flash code, using high performance computing to do laboratory astrophysics. We also have, I forgot to mention, extremely good integration with the department, and part of the department's administration is actually part of the FLAS Center. Jenny Oliver is our administrator, so feel free to reach out to her for information about the FLAS Center. And Ebenezer and Dave are part of the folks that are helping us with our infrastructure and IT support. Okay, so thematically, the research that we're doing at the FLAS Center is mostly geared towards HDP and high-energy density laboratory astrophysics, HEDLA. And you can see here the 3 of the major areas where we're working on actively in terms of the lab astro, ranging from astrophysical jets, studying their stability and collimations using laser-driven experiments, to the study of fluctuation dynamo, turbulence, particle acceleration, and transport, which I will talk a little bit about today. And also shocks and hydrogen and HT instability, so more fundamental physical processes, which you can model with laser-driven experiments. Now, the work that we're doing is done in collaboration with numerous academic partners throughout the US and the world. I don't expect you to be able to read this. It's just to showcase that we're working on a broad range of problems with a very diverse set of academic groups in the UK, the US, in France, and so on. But also with a very strong partnership with the national labs, both in the US and, of course, Los Alamos and Lawrence Livermore, who have been supporting the HDP initiative that has made Flash an HDP-capable simulation code, but also the Naval Research Laboratory, as well as labs in the UK and in France. So Rutherford Appleton and Lully and the LMJ facility in Bordeaux. Apart from developing the code and doing the research, we also have a very strong community engagement, and where we strongly believe that in order for the Flash code to thrive and our work to continue is to engage with the community and enable the science and the research that different groups do in the US and abroad. For that reason, we hold frequent workshops and tutorials. And one of the things that we have instituted is essentially a biennial rad hydro workshop that we're doing in the context of the high energy density science summer school. And Miriam, if you're here, it would be useful to add the link in the chat, because we do have another HDSSS school lined up for the summer. So feel free to check it out. And this is where we essentially train young scientists from graduate students to postdocs to research scientists into how to use and develop rad hydro simulation codes using Flash as a testbed, but also other codes as well. Apart from that, since 2015, we have also instituted a very strong apprenticeship program at the Flash Center, in which the concept is you have postdocs and graduate students and scientists from other groups sort of spend a significant amount of time at the Flash Center, be trained by the folks that work at the Flash Center in order to use Flash for their experiments and simulations. So this has been a very successful program, and more than 30 scientists have actually taken advantage of this. A subset of them you can see here, and many of them end up having careers at the national labs and so on. And therefore, we're creating, in a sense, a very distributed talent pool by creating small nodes of Flash development and Flash use for an NSA and academic groups to be able to recruit from. And of course, we have a very strong presence in conferences and international meetings where our students and our postdocs go and present the work that we're doing. In a nutshell, the work that we're doing tries to combine big laser facilities like the Omega Laser Facility, the National Ignition Facility, to big computing facilities. So like CORI and MIRA at Office of Science laboratories. Under the umbrella of the Department of Energy, we're trying essentially to provide high-performance computing modeling capabilities to academic HDP groups that previously did not have such an access. Okay, speaking of capabilities, now let's switch gears and talk a little bit about what the Flash code can do and what it includes in terms of capabilities. Flash is a portable and scalable application code that is built in such a way that it is composed of units. Essentially, it's a very modular code that you can select a subset of its capabilities in order to create your own simulation. In terms of the code itself, it's a pretty big code. It's written mainly in Fortran 90, more than 1.2 million lines. And thankfully, 25% of those 1.2 million lines are inline comments. And therefore, this allows us to maintain a good understanding of what's what and where things are as new people come to the center and continue the development. Apart from the infrastructure unit that allow you to configure the simulation, have mesh management, do parallel I/O and monitor, we have a number of physics capabilities that have been developed through the year. Now, as some of you may know, the Flash code was originally developed in order to apply it for astrophysical problems. So Flash code versions 1, 2, and 3 were essentially geared mostly to being able to model thermonuclear supernovae, and therefore the original capabilities of the code were geared towards hydro and MHD, equation of state, nuclear physics that you would include in such a simulation, things like self-gravity and material properties and cosmology. But it was about the time when the National Ignition Facility was coming online, when the USDA and NSA reached out to us, and Don in particular, in order to make the Flash code into a publicly available simulation tool for the academic HDP community. The concept being that in order to be able to run experiments as academics in the programs like the Discovery Science program that we have at the National Ignition Facility, one would need to be able to simulate experiments there and therefore have the required capabilities in order to accurately model with some fidelity proposed experiments at the National Ignition Facility or the Omega Laser Facility and so on. So for that reason, we entered a race of development that essentially doubled, if not more, the capabilities of the code in order to be able to do high energy density physics. And this has allowed us to incorporate things like 3 temperature solvers for hydro and MHD, a number of high order that is the bread and butter of Adam Reyes, our code group leader, as well as things that are relevant for HDP, like heat exchange, like flux limited multi-group diffusion, laser energy deposition, implicit diffusion, extended MHD, multi-material EOS and opacities, as well as a number of synthetic diagnostics. So I will touch on all of these a little bit while we go on. Now, the reason for this development is when you're trying to model laser-driven experiments, if you're using systems of equations like ideal MHD, single temperature, you will be missing out on a lot of the physical processes that take place. you have effects like the laser energy deposition only affecting the electrons, or you have shock heating only affecting the ions for the timescales of the experiment. So it's important to be able to incorporate these capabilities. So the way that we went about to do it is essentially maintain the single fluid approach that we were using for hydrodynamics and magnetohydrodynamics, and extend it to 3 temperatures. And this was done in collaboration with scientists at Los Alamos National Lab, and hence we called our 3T extension RAGE-like after the simulation code that is being developed at Los Alamos. And essentially couple your usual continuity momentum induction and generalized continuity momentum induction total energy equation with internal energies for the ions, electrons, and the radiation. And on top of that, add effects like thermal conduction or things like heat exchange between the ions and electrons, as well as the multigroup radiation diffusion solving, which couples the radiation energy to the electron energy. On top of that, there was, of course, also the need to incorporate closures that would be accurate for the materials that we were considering to model, and therefore we have included capabilities of reading tabulated equation states, like the ones that you would have with ion mix or Propaceos or Sesame tables, and on top of that, we have also worked a lot to incorporate capabilities in terms of the radiation transport and be able to model the opacities of a number of materials. Another key thing that we had in terms of the development, and you can see it hidden here as Q laser in the energy equation of the electrons, and the source term in the total energy equation, is the development of a laser energy deposition package, which is based off of the work that Kaiser did back in 2000. It's essentially an optical laser ray trace that allows you to introduce energy to your system by a laser deposition, having rays propagate through the domain and deposit energy using inverse Raman. The laser beams are actually fully configurable. It allows us to have a number of different spot size, a number of different wavelengths, and intensity in order to match a realistic laser configurations. We also allow for 3D and 2D modeling of rays. So essentially you can set up 3-dimensional laser rays and have them mapped onto a 2-dimensional simulation if you're doing a 2-dimensional simulation. More recently, we've actually worked a lot with folks at Prism. This is a company that develops simulation software and tools for the HDP community, to integrate our laser deposition package to their VisRAD software. Essentially, now we have output from VisRAD, which can be read into a script by the flash code and set up the laser configuration in a painless fashion. Now,
Petros, can I ask a question?
Yes, Warren.
Yeah, if you go back a slide, or one more.
Oh, yes.
Maybe you could comment on what is in Flash versus what is in some of the, the ICF codes. Some are obviously classified. So what physics and capability is in each? Maybe just summarize that.
That's a bit broad. I mean, the capabilities that we have developed for Flash are such that I mean, one would need to be very specific what type of comparison.
Let me ask you. I was going to ask this similar question. My understanding is Flash has inverse Bremsstrahlung, right? When you're talking about 10 to the 15 watt per centimeter square, you have nonlinear effects. So do you have those effects in Flash? If not, are you going to include those?
The answer is no. And we don't have any plans to including them right now.
Okay.
And
So I guess maybe related was sort of like if I strip away, let's say, the radiation hydro, if I look at this first set of equations, you've got density, momentum, but you also have magnetic field generation. You've got some sort of an Ohm's law. Are the way you're doing, and then you're trying to add mesh refinement, are things for those sets of equation, is there similarity? Or because of the other things they need to include, it just becomes so different that it's just very hard to answer the question.
Right. So I will actually touch on a few things in subsequent slides in terms of the adaptive mesh refinement and the MHD. But essentially, you can think of a fundamental hydro or MHD solver coupled with a number of operator split operators. So a number of them are essentially treated in a much different way than you are solving your reconstruct solve average technique. So not all of them enter in the Godunov fluxes, not all of them. So it's a mixture of modality that I'll explain in a little bit.
Don has his hands raised. Don, please go ahead.
Oh, yes. So I'm just second what Petros said about, it's very hard to compare these codes in part because there's things we can't say about the lab codes, but we can say something about the flash code, and that is it's designed for the academic high energy density physics community and for laser experiments and other kinds of applications. And so we can say, Petros and I can say that there are certain things that are not in flash and we will not have in flash. And so Petros mentioned sophisticated radiation transport. We could also say very quickly that neutronics and materials properties are not in flash and not going to be in flash. So those categories, can also maybe help just to answer your question, Warren, and yours too, Farhad.
Thank you.
Very good. So responding immediately to what Warren was asking, this is how we do MHD in flash. So the code is actually solving the induction equation using a staggered collocation of the magnetic field. This is the CT method which was pioneered by Balsara and Gardner and Stone. The way that we're doing this is essentially we're propagating in time a magnetic field that is collocated at the cell faces or the cell edges in 2D. And therefore, we're able to use the Godunov fluxes that we are calculating from our typical Riemann solves in order to construct electric fields and use those in order to essentially create circulation theorems on its face and maintain divergence of the magnetic field equal to 0 to machine accuracy. The technique can be found in this paper by Dong-Wook Lee, and it's actually a basis onto which we were able to expand a lot on the extended MHD capabilities, both in terms of an explicit integration by essentially taking the extended MHD fluxes and adding them onto our Godunov fluxes and therefore be able to incorporate them seamlessly into the CT scheme. But we are also doing this, as I said, in an operator split fashion for specific applications. And as Warren predicted, this is done in using adaptive mesh refinement. And this has, as a result, a much raised degree of complexity, as you can imagine, by having different collocations on each given cell. So the way that we're doing the refinement and adaptive mesh refinement is supported in Flash in 1, 2, and 3D Cartesian, 2D cylindrical in RZ and RFE, and as well as a 3D Cartesian cylindrical implementation that we have now, as well as 1D spherical. Adaptive mesh refinement is done using paramesh, which is a block structure octree. So say that you have essentially a feature that you want to have resolved by your mesh. Essentially what we're doing is we're creating higher levels of refinement where the feature is according to given criteria, and therefore have a higher resolved feature and therefore more accurate results. As you can imagine, there is special care that needs to be taken when you have abutting refinement jumps, as well as in order to make sure that the electric fields in abutting blocks are actually adding up to the correct electric field. So there's a lot of overhead included in this approach for that mesh refinement, but it's actually the easiest logical way of us to incorporate AMR in Flash.
Can I ask? Sorry to interrupt again. So do you ever have to worry about, let's say, if you have shocks, different dispersion properties across different resolution regions, and you get anomalous reflection and processes like that? How do you, if you do, how do you handle that?
So that's a very good question, Warren. I mean, a key thing that one needs to be careful of is how to treat shocks in terms of refinement jumps. I mean, if you have shock propagating through a refinement jump and then going out of it, you will have problems with that. Adaptive mesh refinement allows you to avoid that. So it's not a statically fixed refinement pattern, but at each time step, we're making sure that we're capturing essentially features that are characterized by the shock properties like density and temperature and pressure. So we can actually follow the feature around and not worry about effects that like the ones that you mentioned. So one does need to be very careful when trying to model these things.
Thank you.
Now, extended MHC. So in the past year, we have worked, I mean, one of the good things about the pandemic is that we were stuck in our homes in front of computers. And this is good only if you are a computational physicist. As a result, we were able to drastically expand the MHC capabilities of the code in order to incorporate essentially all of Braginski terms in the explicit fashion. This was an effort that was spearheaded by Eddie Hansen, and he was helped by folks at the center. As of now, we have the capability to have Hall, Birman Battery, Nernst, Ettinghausen, Maggi, Rigg-Leduc, and CMEC, as well as an anisotropic implementation for magnetic resistivity. Also, in the past year, in connection to the ARPA beta project that I will talk about towards the end of the talk, we have worked to have essentially the most up-to-date transport coefficients for electrothermal resistivity and thermal conduction. This is based off of the work that Jonathan Davis, Han Wen, and Jian Held did recently, published in 2021 on physics of plasma, where essentially, and this is the reference, full reference if you're interested, where essentially they used Fokker-Planck simulations using the Ocean code, as well as the results of previous studies by Jian Held and the expansions that they had done for the Likert polynomials to recover essentially new fits for the perpendicular resistivity and perpendicular electrothermal coefficient. And these are now incorporated in the code. To further increase the fidelity of transport, especially in cases where strong magnetic fields can inhibit thermal transport, we have also developed an implicit anisotropic thermal conduction implementation for Flash, which is now cognizant of the direction of the magnetic field. The thermal conduction capability in the code up until now has been one that is completely agnostic of what the magnetic field looks like. We have coupled this new implementation with the transport coefficients by Jian Held, the previous paper from this one, if you will. And all of this is operating in the code right now. You hear me talking a lot about implicit this, implicit that. This is one of the operator splits that we're doing in terms of how we're solving the equations. What we're doing in Flash is leverage essentially Lawrence Livermore's hyper library of preconditioners. It's essentially a nonlinear, it's a sparse matrix algebra solver that Falgut and collaborators have developed at Livermore and have been continuing to develop in the past 20 years. More recently, they are actually developing it for accelerators and is capable of taking advantage of GPU accelerators in US architectures. The reason why we're doing this is because when we're considering cases of cold magnetized plasmas, the implicit time step turns out to be usually what the parabolic time step turns out to be what defines the time to solution. And this is easy to see how, since the parabolic time step is scaling as delta x, the resolution element squared, rather than the hyperbolic, which just scales as delta x, if you have high resolution, quickly you will end up having your parabolic time step dominate the run. So this new implicit solver essentially has been tested, and you can see here the simple diffusion in cylindrical coordinates and compared against to the explicit implementation that we have in Flash, being able to match the result exactly. And also, this is the effect of ohmic heating essentially captured by the new implicit implementation. Just a note for this 1D benchmark, the speed up in terms of time to solution is 400x, just due to the fact that the time step, the evolution time step was essentially defined by the parabolic time step. Okay, so this is sort of like a bird's eye view of the Flash code capabilities. Now let's see a little bit about its applications. And the first one that I will talk about has to do with the laboratory astrophysics effort that we're doing in collaboration with the University of Oxford. This is the turbulent dynamo collaboration, and the lead at the University of Oxford is Gianluca Gregori. His team and us and folks at the Flash Center, as well as a number of other people from numerous institutions, including national labs, have banded together in order to study magnetized turbulence, fluctuation dynamo, as well as cosmic ray physics. The thing that we're trying to answer has to do with the origin of cosmic magnetic fields. And one of the key processes that is thought to be responsible for the magnetization that we can now measure in galaxies and galaxy clusters is that of fluctuation dynamo. In a very brief description, fluctuation dynamo amounts to essentially your turbulence picking up your magnetic fields and inducing to it topological transformations. You can think of magnetic field loops being stretched, twisted, and folded, and essentially transferring kinetic energy from the turbulence into the magnetic energy that we have in the turbulent magnetic field. Now, studying this in the laboratory is actually a really hard thing to do, because a key process, a key requirement for this process to work is for the magnetic Reynolds number, or essentially your resistivity of the plasma to be small enough, the resistivity or the magnetic Reynolds number large enough for the motions essentially to have flux frozen in magnetic field. So we started a long-term effort with the T-Dyno collaboration, starting with experiments at smaller laser facilities like Vulcan at Rutherford Appleton or Lully, in order to build essentially an experiment that would allow us to study fluctuation dynamo in the lab for the first time. And this is a mechanism that has been theorized since the 50s and has been simulated since the 80s, but up until our work, it had not been proven in the lab. So in order to be able to reproduce dynamo in the lab, what we did is essentially a year-long campaign with Flash simulations in order to design a target for the Omega laser facility. And through the NLUF program of the USDA and USA, we were awarded time at Omega, and we were able to do the experiments that I'm about to describe. the concept is the following. What we're doing here is we have a very small target, which you can see here on the bottom left, and here's the schematic of it, which consists of a pair of target foils and a pair of grids. The target foils are actually compound targets, which include a washer and a small thin plastic disc, which were designed using Flash. Ab initio, we had a blank slate, and we came about with this complex configuration that the folks at GA were kind enough and skillful enough to put together for our experiment. So this target is the size of a dime, and what we're doing is we're essentially ablating the back of it using the Omega laser and about 5 kilojoules of energy on each side, which results in essentially oops, awesome. Need to move a little bit the I'm trying to move a little bit the there you go. So what we're doing is with this laser drive, essentially what's going on, you have Bigham battery generation in the back of these targets, right? And the targets, due to the rocket effect, the drive creates shock that breaks out from the target and then propagates towards the center of the experiment. By design, we have placed a pair of grids that are misaligned in space in order to create an asymmetry in the collision of these two plasma plumes. This asymmetry results in essentially in interleaving plasma fingers that shear and become hot enough in order to get magnetic Reynolds numbers of the order of many hundreds to thousands initially, which is above the critical limit for dynamo to operate. Now, the cool thing about this experiment is actually we're taking advantage of Bigham battery magnetic fields generated by the laser target interaction that are being advected, flux frozen into the plasma onto to the turbulent interaction region in the center, where they're acting as seed fields for this amplification. Now, this is essentially what the simulations were predicting. So magnetic Reynolds numbers above the critical limit for dynamo to operate, as well as dynamo amplification in the center of the experiment. But it was the experiment itself that actually was able to demonstrate dynamo for the first time at Omega. So here you can see a snapshot of some of the diagnostics that we're using. We have X-ray imaging, we have proton radiography with a D-helium-3 capsule, as well as Thomson scattering with this green probe over here, in order to be able to measure the properties of the plasma that we're generating. And the X-ray imaging sort of gives you, these are soft X-rays being emitted by the hot plasma. It gives you an idea of the structures that we're able to create. And you can see that in premise, the shape of it matches fairly well with the Flash prediction. The analysis of the X-rays actually allows you to connect the fluctuations in the X-ray intensity to the fluctuations of density. This is a trick picked out from the astronomers' bag of tricks, and we were actually able to show that the turbulence that we're generating in the center has the same power spectrum as Kolmogorov turbulence, so -5/3. So using Thomson scattering, we were able actually to verify that the magnetic Reynolds number is large enough for dynamo to operate, but it was our magnetic field diagnostics that allowed us essentially to demonstrate the amplification of the field from very small seed field values to values that are comparable essentially to the kinetic energy, which is the hallmark of the dynamo amplification. And you can see here proton radiographs essentially we're imploding a D-helium-3 capsule on the side, creating a bath of protons going into the interaction region, being deflected by the magnetic fields, and then recorded on a film. And these are essentially snapshots of magnetic field topology that you're getting. We actually were able to reconstruct. We developed techniques to reconstruct and do the inverse mapping essentially from the proton radiographs to the magnetic field, the path integrated magnetic fields that the protons felt, and we were able to measure the magnetic field as a result of the dynamo action. So this was a big deal. The academic press picked it up, and as Farhad mentioned, we were also awarded the 2019 John Dawson Award for Excellence in Plasma Physics Research. The reason why I'm putting this quote is because this really has opened a new path to laboratory investigation of other astrophysical processes, and our collaboration has launched a multi-institutional, laser facility, multi-year effort to study fluctuation dynamo, magnetized turbulence, as well as astrophysical processes that are mediated by them. One of the things that I wanted to showcase in terms of Flash and what you can do with the code for laser-driven magnetized experiments is things like validating your results from your experimental diagnostics. So these are two snapshots of X-ray imaging at early time when one of the two flows was protruding from the grid, and you can see the matching in time that we're able to make. And this is a snapshot right before the collision. We have also worked a lot again with Prism, and now FLAS is actually a native input for Spec3D. So it's rather straightforward to take the simulation of your experiment and create synthetic X-rays from their software. And this is a comparison between the real X-rays and the synthetic X-rays that we derive from Flash. Other things that you can do is use optical Thomson scattering. This is us capturing essentially the merging of the two flows by seeing the merging of the optical Thomson scattering signal. And we have also developed a synthetic optical Thomson scattering diagnostic, which allows you to create a synthetic signal which can be compared then to the actual. But the most important one is proton radiography, and we have included now in Flash also proton radiography module that you can create synthetic radiographs, which you can then process as you would your experimental data to recover the path integrated field, allowing you to make a comparison on the same basis as you're doing with the experiment. And also we have included Faraday rotation capabilities, which is the other diagnostic that we filled in. Now, as I said, this has launched an effort that has not finished yet. There is a number of things that we're working on right now. The most recent study that we published was at Proceedings of the National Academy of Sciences in 2021. Archie Bott was the lead author on this one, where essentially we presented the first time resolved measurements of turbulent dynamo in the Prandtl number order unity and a little bit above the Omega laser facility. So this is a viscosity dominated turbulence, which is applicable to things like galaxies and galaxy clusters. So just by small modifications and guided by the class simulations, we're able to reach that regime as opposed to the small Prandtl number regime that were in our previous experiments. And here you can see the simulation of the modified target. This modification allowed us to have a high cadence of shots, and therefore actually able to show you movies of the experimental data rather than the simulation data, where you can see the evolution of the X-ray images, all of these taken from different shots, of course, and also the evolution of the proton radiographs and the path integrated magnetic field. One thing that this allows you to do is actually capture the evolution of the mechanism as a function of time. And these time resolved measurements allow us essentially to quantify the magnetic field growth rate. So the onset of turbulence, and I challenge you to tell me which of the two columns is Flash and which is the experimental one. Well, the left is the experiment, the right is Flash. So we can actually see both in the experiment and with the Flash simulations how the turbulence evolves, establishes, and how quickly we get to the Kolmogorov scaling that we talked about earlier. The plasma characterization was key in this one. Having Flash while doing the analysis of the experiment has been paramount, because it allowed us essentially to understand in detail what our diagnostics were telling us. So using Thomson scattering, we're able to get temperatures, volumes, electrons, the velocities, turbulent and bulk as well, and the electron density as a function of time. So we can actually now have time plots of things like the velocity, we're plotting here the turbulent one, the temperature, the density, and therefore have a time history of key non-dimensional parameters like the fluid Reynolds number or the magnetic Reynolds number. So our results demonstrated that early on, when the bulk of the amplification is happening, we are in the Prandtl number above unity regime. We also were able to show that measurements at late times should be taken with some caution, since we were able to show that the Thomson scattering diagnostic that we were using, which is a laser probe, actually can heat up the plasma significantly, and this is one of the effects that are included in the diagnostic in Flash. That essentially cautions you, if you have a very cold plasma and you're probing it with the laser, you might be measuring essentially the effect of your probe rather than what is actually going on in the experiment. But the results showed that we have Prandtl number of the unity dynamo operating in, and again, the cadence allows us to see the field evolution. So you can see the seed fields at early times and the formation of these strong stochastic filaments as the magnetic field is being amplified. So we can actually create the time history of the magnetic field and the magnetic energy. And here you can see plots of essentially the predicted RMS field by Flash, and the points are the values that we get from the experiment. And these are the peak values, the maximums bounded by the experiment. One thing to note here, so in short, I mean, this experiment was able to show us that we have a magnetic energy amplification of 3 orders of magnitude. So dynamo operating at, and it's consistent with predictions of driven turbulence simulations. But what was not consistent was actually the growth rate. So what we found was that the magnetic field growth rate, especially in the initial kinematic phase, the growth rate was actually a factor of a few larger in the experiment and the Flash simulation, rather than what was being predicted in the driven turbulence simulations. So that's something to think about. It means that dynamo might actually be a more efficient mechanism than what was expected. But again, to showcase, one thing that we found was that the actual scale, the integral scale of the fluctuations in the Flash simulations was the only thing that was not matching exactly what we were seeing in the experiment. And this is something that has been a long-standing problem as people try to explain the tangled magnetic fields present in the ICM using driven turbulence simulations. And we have put forward a number of possible explanations, but this is something that we will be looking into for more detail in upcoming shots. But again, the ability to simulate our magnetic diagnostics has been key in order to evaluate the effects of these magnetic diagnostics in our measurements. Okay, so
10 minutes, Petros.
10 minutes. Thank you. I'll be on time, I promise. So the next thing that I want to touch about is the work that we're doing in the context of CMEC, the Center for Moderate Extreme Conditions. This is DOE and NSA Center of Excellence that is hosting us for these seminars. And it's essentially studying the properties of matter at extreme conditions, things like energy transport and HDS systems, things like material properties, and combining them into understanding more complex systems in nature under conditions that you would find inside planets or among the stars. The work that we're doing for CMEC amounts to essentially assisting many of the experimental projects that we're doing, both with laser-driven and pulse-driven plasma experiments, providing Flash simulation support. And on top of that, in our work is also the expansion that I talked about earlier of the non-ideal MHC capabilities of the code to include things like Hall, Nernst, and implicit resistivity. We're also working on expanding the Flash capabilities to simulate Z pinches, which is something that was started and spearheaded by Marissa Adams, a graduate student at the Flash Center, who has developed a new unit that essentially allows you to implement power drive in Flash in the form of a boundary condition. So essentially one could take standardized current profiles like the ones you have on Cobra, and the code essentially transforms in each time step the current into a magnetic field boundary condition that is what is employed in other codes like Orgon and Perseus in order to have an effective current drive and be able to model things like wire arrays and Z pinches and gas pumps and so on. This also sets the stage for the current circuit implementation, which is something that is in our work plan, and we will be doing with collaborators both at the LLE and other institutions. The current drive now has support for 1D, 1 and 2D cylindrical geometries, as well as 3D Cartesian support, which we are trying to finalize right now. This is just one of the validation benchmarks that we did for the analytical solutions of sleuths. You can see here the plot on the right is the 0D result that go to the arrows so I can actually move things around much more quickly. So you can see here essentially the theoretical trajectory of a simple implosion, a cylindrical implosion on top of the Flash predicted trajectory. So we have validated the implementation, and the results are now being prepared for publication that Marissa will lead, and the new model will be made available with the next Flash release. With the help of San Diego and the team that Farhad leads, we plan to use the CSAR results to actually validate the Z-pinch capabilities of the code, and these are just snapshots. Thanks to Fabio for providing them, that we will be using to model this. Two more other experiments that we're helping the CMEC with. This is a new collaboration that we started now with Jess Fulgram, Chris Neiman, and Scott Fieser, in order to do simulations of this high rep rate experiment that they have to measure Birman battery generated magnetic field in space, which is a rather cool experiment, and we hope to be able to help them with understanding the volumetric distribution of their data. And another one which will be coming up in the next talk a month from now by Mario Manuel. We're working essentially on the Axel data that folks at Lawrence Livermore were able to recover at Omega, and essentially use 2D Flash simulations in order to provide input and understanding on the plasma properties of the jets that are being used to study the Weibull instability. Of course, this is a kinetic effect, so these simulations will act as input for other kinetic codes like OSIRIS. And the last case study that I wanted to touch on was the work that we're doing for ARPA-E and BETE. The development that we've done with Flash has actually allowed us to engage with ARPA-E and assemble at the LLE and at the University of Rochester a theory and capability, a theory and modeling capability team to assist different performers in the ARPA-E BETE program. More specifically, we're working with folks at the PLX, the Plasma Liner Experiment at Los Alamos National Lab, the PFRC that Sam Cohen is working on at Princeton, at PPPL, as well as the folks at MIFTY and essentially the stage Z-pinch concept that they've been working on. The codes that we're using are Flash, which is a rad hydro code, Triforce, a code developed by Adam Sefko, which is a hybrid fluid kinetic simulation tool, and as well as Osiris. This is the team. I'm the PI of this project, but I have support from excellent scientists. As I mentioned, Adam Sefcoe, Chuan Ren, Ricardo Betti is involved, Jonathan Davis, Han Wen, John Shaw, and as well as our postdocs, so Eddie Hansen, David Mihta, Fernando Garcia Rubio, Jack Wu, and we have an opening for a graduate student position here for HPC support. Just briefly, the PLX experiment at Los Alamos is essentially a plasma jet-driven magnetic inertial fusion scheme. The idea is essentially to create a spherically imploding plasma liner to compress a target that is all of them being formed with the use of plasma guns, which are being developed by Hyperjet Fusion. And here you can see a photo of the target. So this diameter is about 2.7 meters, and therefore we're talking about much more of a larger scale type of experiment than the ones that I've been showing you. We're using FLAS essentially to be able to predict what the merging of these plasma jets will do. Essentially, there are specific requirements that we're trying to achieve in order to get to fusion conditions. And one of the things that we've been looking at recently has been the effects of isotropic versus anisotropic thermal conduction in the merging, and how that can change the distribution of temperature in the target. What we're getting are results that are very encouraging. We're getting essentially ion hole parameters of about 1 to 10, electron hole parameters of about 100 to 1,000, and plasma betas of order unity, which is essentially what the team at Los Alamos, Sam Langendorf and Tom Baibank were hoping for. So this is a very much ongoing collaboration that it's very fun to work with, and we're really enjoying this collaborative effort. And the other thing that I want to touch on is the first application essentially of our implicit solver for magnetic resistivity, which is showcased here in the state Z-pins concept, where this is a concept developed by folks at MIFTI, so Magnetic Inertial Fusion Technologies. We're talking about Emil Ruskov, Hafiz Rahman, and Paul Ney. The concept here is a state Z-pins, essentially a heavy liner being used to implode the target fuel, and essentially assisting the implosion by shocks in order to reach fusion conditions. This effort is well underway. These are the first results from the current drive that we were given by our MIFTI colleagues, and our first attempts at the implosion of one a xenon liner essentially onto DT fuel. Again, this is very much preliminary, so I will not expand too much about it, but it's a very productive and very fruitful collaboration we have with folks at MIFTI, and we're looking forward to continue this. This brings me to my summary slide. So I want to leave you with the fact that FLAS is a publicly available multiphysics code that can be a powerful tool for modeling magnetized plasma experiments, mostly for the academic HDP community, but also the national labs in the industry are now seeing the benefits of having such a publicly available code to be able to model experiments. At this new home at the University of Rochester, we're continuing the work as usual. We're increasing simulation fidelity and expand the capabilities of FLAS in order to be able to model new problems and enter new magnetized regimes, especially the cold ones, which have been hard up until now. In terms of the applications, Flash in the past 10 years have been applied to numerous experiments, and our ability to be able to model ab initio, the lab astro experiments of the TDynamo collaboration has been key for us to be able to demonstrate fluctuation dynamo in the lab and to continue this work. Now, all of this development has enabled a number of other research trusts, both in terms of CMEC and also our work that we're doing with ARPA-E BETE, as well as other projects that I have not time to talk about, but essentially we're trying to push the boundaries on the applicability of the code and apply it to new and cutting edge and exciting science. So with this, I will thank you and I will take any questions.
Thank you. Let's thank Petros virtually. Any questions for Petros? I have one in the chat. I believe you did answer, but I will read. Are there any plans to release a version with additional MHD capabilities?
Oh yeah, yes, absolutely. As soon as we finalize the agreements with Chicago to have the new release from Rochester, you can expect a very much extended MHD capability release that will be Flash 4.7.
Any other questions?
Yes, but I expect essentially all of these guys.
I have one question, Petros. Do you have any plans of adding atomic modeling? For example, you were saying that you are working with PRISM folks.
So in terms of atomic modeling, no. So what we're doing is we're taking advantage of the tables that they can create, and provided that actually if you have a license to Propaceos, we can provide essentially readers to our Flash users to take essentially the output of Propaceos, so EOS and opacities, to incorporate in the runs. But on-the-fly calculations is not something that we will entertain.
Okay. Any other questions for Petros? Okay, I don't see any more questions. Thank you so much, Petros. We appreciate your time for an exciting talk.
Thank you, Farhad. It was a pleasure giving this talk, and thank you all for your attention.